Okay, increasing, decreasing versus remaining constant for a function. What I want to do first is just explore a quadratic and talk about why it's very important that you understand what values to use when you're talking increasing and decreasing. So, say this was at the coordinate point, well, I kind of drew it on the same scale. Well, I'm going to pretend that the scale changed. Let's make that 5 and let's make this 2. Okay, so different scale on the x and y axes. If I asked you, I don't like that. It's easier when it's intuitive. Okay, so I'm going to draw it like over here. Still kind of draw it the same. I'll make this 3 and that 4. That's good enough. Okay, if I asked you to tell me what the function is doing, even though the arrow is pointing up, if you graph from left to right, it starts from up here and it actually graphs this way, right? So it's decreasing and then it's increasing. But the problem I have with that is I have a lot of people that'll say it's decreasing from positive infinity down to 4, and then it's increasing from 4 to positive infinity. And while I agree that that is true information, it's not unique. Infinity to 4 and 4 to infinity are the same range of y values. So while that is important to tell me, like, you know, especially if you're looking at y values, I mean that's your output. You want to know what your range is from. The question is, when am I increasing and decreasing? When is x? There's only one thing this function is doing for all x's between negative infinity to 3, and that's decreasing. And there's only one thing the function is doing from 3 to infinity, and that's increasing. So decreasing would be from negative infinity to 3, and then increasing would be from 3 to infinity. And the reason why I don't include 3 with a bracket is because I'm neither decreasing or increasing at that moment. At that moment I have stopped. Okay? Furthermore, if I put brackets right here, then that would be implying that I'm both decreasing and increasing at that point, and I find that to be problematic. Now, I did ask you to draw a function that is increasing, decreasing, and remaining constant, and so that's not like a natural function. This is something where you're going to have to do kind of a piecewise thing. So I'm going to kind of put it together. I'm going to have like a quadratic type shape, and then coming up, and then let's have it remain constant thereafter. Okay? So since I'm just making stuff up, I'm just going to pretend like this x value is, let's say, let's go with 5, and then we could make that 3. Now, notice how I'm not labeling the y values because I truly don't care as far as like when a function is doing something. I care about the x-axis. I care that it goes from negative 5 or negative infinity until 5 doing negative 5 doing something, and then from 5 to 3 I'm doing something else, and then from 3 to infinity. And the reason why I labeled this is because that was a turning point, and so is this as far as like changing behavior. Because I know the first thing the function is doing is decreasing. So I would say decreasing from negative infinity to negative 5. If you just put a d, that's fine. And then I know the function is increasing. So the function is increasing from negative 5 until 3. And lastly, the function is remaining constant. So it would say constant from 3 to infinity. And there you go. So some kind of function where you're doing all 3 things, and just make sure that whenever you do decreasing and increasing constant, only x and only parentheses. Only x, only parentheses. Alright, let's do 8. 8 says, how do you add fractions, multiply, divide? Make up examples for each. So add, I guess I should say add, subtract, because it's the same type of thing. If you're trying to add or subtract fractions, then you must have common denominators. The only way that I can add 2/5 and 1/5 is because they have the same denominator. I'm comparing the same amounts. 2/5 plus 1/5 is 3/5, right? If I had 2/5 thirds plus 1/15, right? These are not the same denominators, so I cannot compare these amounts and just say, well, I'm just going to add the denominators, because it definitely does not translate in the same way. What you need to do is have a common denominator, so you'd multiply top and bottom by 5 on this, and that would give me 10/15 plus 1/15. Now they're in the same proportions, right? 10 out of the 15 plus 1 out of the 15 is 11 out of the 15, so I can add that. And then lastly, what if they share no common factors? What if I was adding 2/5 and 1/3? Okay, no common factors, so what I'm going to do is I'm going to multiply by each other. And that would end up being 6/15. Now this is requiring me to know how to multiply fractions, right? Because 3/3, and then that's technically what I'm multiplying, 3/3 and 5/5. But okay, 6/15 plus 5/15, and that would end up being 11/15. Okay, so you have to have the same denominator. You have to have common denominators in order to be able to add, subtract, or add or subtract fractions. So obtain common denominators. Okay, now how do I multiply fractions? Because here's what I see a lot of. If I give, in the course of working a problem, students have to multiply 2 times, let's say 3/5. A lot of times students will write 6/10. But the problem I have with that, if you think about 6/10, 6/10 is equivalent to the fraction 3/5. So you multiplied the top and the bottom by 2. You didn't do anything to it. You just rewrote in a different way 3/5. You spelled it in a different way, if you will. So in fact, when you multiply 3 out of 5, well, I'm going to change that to 1 out of 5, just to make it a little easier to understand. If I had 1/5 of something and then I doubled that, then I should have 2/5 of it, right? Which is why you actually multiply by 2 over 1, and you multiply numerator with numerator and denominator with denominator. Okay? So, numerator with numerator, denominator with denominator. Okay? That's how we multiply fractions. And I know I'm not writing these out in sentence forms, but we can. This is shorthand for us to remember things. Okay? If I am trying to divide fractions, so I believe I've talked to most classes about this, but just in case, especially if you weren't here or in the Google Meet. If I ask you to divide 2/3 by 1/7, most students know what to do. You know, keep, flip, change, you know KOC, you know to remember to multiply by the reciprocal, you've memorized that. 2/3 times 7 over 1. And I agree, that is true. But I want you to make sure that you understand the algebra behind it. If I ask you to divide 2/3 by 1/7, the reason why it's equivalent to 2/3 times 7 over 1 is because if you're dividing a fraction by another fraction, if you multiply both the numerator and denominator by the reciprocal of the denominator, what this allows, and remember, we can do that because that's 7 over 1 over 7 over 1. That's something divided by itself. That's just 1. We're multiplying by 1. This right here, if you multiply straight across, you get 7 over 7, which is 1. And in the numerator, I get 14 over 3. Right? When you divide by 1, though, you don't need to write that down. So, in fact, you just get 14/3. So 2/3 divided by 1/7 is the same thing as 2/3 times 7 over 1. And I'm okay with us jumping to that, but we have to understand why, the algebra behind it, okay? So that is, in fact, 14/3. So if I were to write it out, I would say multiply numerator and denominator by the reciprocal of the denominator. Okay? Let's do number 9. How do you simplify roots of expressions? Give an example and include variables. Okay. Okay. So first off, let's just talk it out. Simplifying roots. If I asked you to simplify the square root of 20, then hopefully what you would recognize is, or remember to do, is that you would want to break it down to 4 times 5. And the reason why is because 4 is the perfect square, right? Then you split it up and say the square root of 4 times the square root of 5. So you apply the root to each individually, and then you can simplify, and then there we go. So as far as the process goes, then what you want to do is you want to factor, and this is called the radicand, what's underneath. Factor the radicand into perfect root and non. Apply the root to the perfect root, or more like perfect power, but okay, so I just said it that way, but then I said perfect root. I'll keep with the root to help, because it's a perfect square root, but it's perfect, perfect square. Let's go with perfect power. Harder to just say into words, but okay. Apply the root to the perfect power and simplify. Okay. Now, let's talk variables for a second. If I ask you to take the square root of x to the 4th power, what we can do is we can think of this as x squared times x squared, and that's the same thing as x times x. The square root of, I'll split it up. The square root of x squared times the square root of x, which is, sorry, the square root of x squared times the square root of x squared, which is x times x, which is x squared, right? Okay, so let's go a little bit further. What if I asked you to take the square root of x to the 8th? So that's 4 x squares, right? So that's the square root of x squared times x squared times x squared times x squared. So that's going to end up being x times x times x times x. That's going to be x to the 4th. So what you have to remember is that there's an understood 2 right here, right? What you end up doing with power, so it's different from the numerical values, right? If you do this, you separate the perfect square. But I'm not taking the square root of 8 to get 4. I'm dividing 8 by 2, because it's like how many times do I have a grouping of 2? So if I asked you to take the square root of x to the, let's go with 7th, right? What I end up with is an x squared times an x squared times an x squared times another x. That's 7 x's in total, right? Well, the square root of x is x, the square root of x is x, the square root of x is x, and then I have 1 left over. So this is like that 5 that's left over, right? It's not a perfect power. In which case I'm left with 3x cubed times x to the 1st power. So if you just ask yourself, how many times does 2 go into 7? It's 3 times with 1 left over, because that's the power of x, not the cubed root, to be clear. Yep. Okay, that was my timer for the video, but I'll finish this one up. Okay, so say I asked you to take the 3rd root of x to the, let's go with 23rd. So here's what I know. 3 will go into 23 7 perfect times, right? So I can have like x to the 21st. And then 2 x's left over, right? So 3 goes into 21 7 times, but then we would have those 2 left over. And so what you're doing is you always take the power, divide it by the root, and whatever the remainder has to remain in the interior. So 3 goes into 23 7 times with 2 left over. Okay. Okay, so I'm going to do one more example with numbers and variables. If I asked you to take the cubed root of, let's say, 16x to the 9th, y to the, let's go with 16th. So first off, the square roots are really easy because we all know we have those memorized. But we do have to start at some point memorizing our cubic, so at least the powers of 3 for a few. I know 1 cubed is 1. 2 cubed is 2 times 2 times 2, that's 8. 3 cubed is 27. 4 cubed is 64. I would expect us to at least have those memorized at some point. So when I think about perfect cubes that I want to separate, I know that 8 is my perfect cubed, and then I would be left with 2 left over, right? So when I think about simplifying that, the cubed root of 8 is 2, because that's 2 cubed, and then I'd have 2 left over. So I'm going to put a 2 on the outside, and I'm going to put a 2 left on the interior. So this is the cubed root of 8, and this was the cubed root of 2 that did not simplify. Okay, now let's talk about the x's. How many times does 3 go into 9? Because that's how many clusters of x cubed I have. There are 3 exactly, so that would just be x cubed. And then, how many times does 3 go into 16? Because that would be how many clusters of y cubes we have. So that would mean we have 5 of those, right? 3 times 5 is 15, and then we would have 1 left over. And so there is your answer. 2x cubed y to the 5th times the cubed root of 2y. Okay, I'm going to end the video there on number 9.